High Level Paper 1, 2011, Time Zone 1. 1.7 grams of sodium nitrate is dissolved in water to prepare a 0.20 litre solution. What is the concentration of the resulting solution in moles per litre? We want the concentration, and the concentration is given by moles per litre. So we must change the number of grams of sodium nitrate into moles. This can be done by dividing the grams, 1.7, by the relative mass, which is given as 85. 1.7 over 85. We call up the calculator. 1.7 divided by 85, and this gives us 0.02 moles. 0.02 moles of sodium nitrate. Now this is per litre, so we must divide by the number of litres. So the concentration equals 0.02, the number of moles, and the number of litres we're told is 0.2. 0.02 divided by 0.2, if you can't see it, 0.02 divided by 0.2, and this gives us 0.1. 0.1 moles per litre. On to question 2. What mass in grams of hydrogen is formed when 3 moles of aluminium reacts with excess hydrochloric acid according to this equation? So we're told that we have 3 moles of aluminium. So the coefficient for aluminium in the equation is 2. 2 moles of aluminium makes 3 moles of hydrogen. So we've got 3 over the number of moles here to multiply by 3 to get the number of moles of hydrogen. So what we're saying here is that if we had 3, if as 2 moles make 3 moles, well, 3 moles is 3 over 2 times 2 moles, and that will make 3 over 2 times 3 moles of hydrogen. Now we must change the number of moles of hydrogen. Let's just put moles in here so we know what we're talking about. We must change the moles of hydrogen to mass. And to change moles to mass, well, moles times relative mass equals mass. So in this particular case, 4.5 times the relative mass of hydrogen. Well, hydrogen has got an atomic mass of 1, so its molecular mass is going to be 1 times 2, which is 2. So that comes to 9 grams. Oh, 93. 9 grams. On to question 3. Relative molecular mass of a gas is 56, and its empirical formula is CH2. Remember the empirical formula? Empirical formula is the simplest ratio. So the relationship between empirical formula and molecular formula is that there is a certain number of empirical formulas, an integral number n, is equal to the molecular formula. Well, the empirical formula is CH2 in this case. So what we've got is n CH2s, let's put it in brackets, n CH2s will equal what? Well, how do we know what the what is here, the molecular formula? Well, the mass, obviously, of CH2 multiplied by n will give you the mass of the molecule. Well, we're told what the mass of the molecule is. It's 56. So what we have here is n is equal to the molecular formula 56 mass divided by the mass of the empirical formula, which is C12 and 2 hydrogens 14, and that comes to 4. So our molecular formula equals 4 times CH2, which is C4H8. Let's move on. Now we need to work out what the sum of all coefficients is when the following equation is balanced using the smallest possible whole numbers. When we balance equations, we should always start with elements that appear once only on both sides. Now in this case we could choose carbon or hydrogen, because carbon and hydrogen appear once on the left, and carbon appears once on the right, hydrogen appears once on the right. So that would be quite valid to start there. We need to keep to the smallest possible whole numbers. Well, hopefully we can see that if we leave C2H2 as it is without a coefficient, that will give us 1 H2O on the right, and that's going to give us an odd number of oxygens. So we need to have at least 2 C2H2s. So let's start off with 2 C2H2. And we don't know how many oxygens there are, so I'm just going to leave it as oxygen for the moment. Now, if we've started off with 2 C2, that's 4 carbons, so we must have 4 carbon dioxides. And we've got 2 H2, so that's 4 hydrogens, which is enough for 2 water molecules. Now let's add up the oxygens we've got. Well, on the right hand side we have 4 CO2, 2 H2O, so there's 4 O2s, which is 8 oxygens, and 2 O's, which is 2 oxygens. That makes 10 altogether, so that's telling me that I have to put a 5 here. So the sum of the coefficients is equal to 2 plus 5 plus 4 plus 2. And we can see that comes to 13. Question 5. The electronic configuration of vanadium. Well, no one expects you to know where vanadium is in the periodic table, although you probably remember that it's in the transition metals. Fortunately though, we've always got a periodic table to hand. So let's have a look at the periodic table and find vanadium. Well, vanadium is in the transition metals. There we are, element number 23. And that means that all of the shells in the first, the second and the third periods are full. And if we go to the right over here, we can see that the full shells are represented by argon. And so we can start by putting argon in square brackets, and that represents the electronic configuration of argon. And then after argon, well, we have a look and we'll see that there's 4, that we're in level 4 here, and it's level 4 s electron 1 s electron 2. So that's 4s2. Now the next electron's in the 3d level. So this is 3d1, 3d2, 3d3. So to complete the electronic configuration, it will be argon 4s2, 3d3. Which quantities are the same for all atoms of chlorine? Well, the number of protons, yes, number of protons, true, because the number of protons gives us the identity of the element. What about the number of neutrons? Is this true or false? Well, chlorine has 2 isotopes, and isotopes have different numbers of neutrons. So this cannot be true, this must be false. 3, well, the number of electrons is equal to the number of protons in all atoms, in all neutral atoms, not in ions, but in neutral atoms. So this is also true. So the answer is 1 and 3. Which property generally decreases across period 3? Well, what have we got? We have atomic number, electronegativity, atomic radius, and first ionisation energy. Well, the atomic number, if we look across period 3, this is period 3, goes from 11, 12, 13, well, this is increasing. We know the atomic number increases as we go across a period. Electronegativity. Well, electronegativity increases to fluorine, so it increases towards the right. Fluorine is the most electronegative element. Atomic radius. Well, as we go across the periodic table, we're adding in protons to the nucleus. This makes the nuclear charge greater, and the pull or the attraction on the outer electrons becomes greater as well, and this shrinks the size of the radius. So in fact the radius gets smaller as we go from left to right. And to cover ourselves, the electronegativity, we had that, the first ionisation energy, well, sodium's got the lowest, magnesium has got a higher one than sodium, and gradually it doesn't increase linearly across the periodic table because of the different types of orbitals, but there is a general increase across the periodic table. So our only possibility here is the atomic radius. So the answer is C, atomic radius. Next question involves group 7. Involves the oxidizing ability of group 7. Well, the thing to remember here is that fluorine is the strongest oxidizing agent of all of the elements. And so, as fluorine is at the head of this group, this means that fluorine has the tends to get reduced, it oxidizes. And the rest of the elements follow the trend going down. So they become progressively less good as oxidizing agents. So we can discard D, for example. D is impossible. We can't say that iodine is not a stronger oxidizing agent than fluorine. Bromine will oxidize chlorine. Well, no, it can't, because chloride ions. It can't, because bromine has got to be a weaker oxidizing agent than chlorine. We've already said that fluorine has a fantastic tendency to be reduced, so B is incorrect. So it looks like we're on C. Let's check C. Chlorine will oxidize iodide ions, and this is true. Chlorine reacts with iodide ions in this way to give chloride ions and iodine. Which electron transitions are responsible for the colours of transition metal compounds? Well, the transition metals are coloured all except for scandium and zinc in their compounds. Well, this suggests there's something about the electron distribution of these central D transition metals which isn't shared by scandium and zinc. And the answer is they have partially occupied D shells. So when we have a partially occupied D shell, we can have transitions between D orbitals. In fact, they're electron transitions between non-degenerate D orbitals. And the energy of the light that is absorbed is equal to the difference in energy between the D orbitals. Remember, this term non-degenerate means not having the same energy. Next question, how many S and P bonds, or sigma and pi bonds, are present in a molecule of propyne? Well, the answer here is that we need to look at the structure of propyne. CH3CCH. Hopefully we remember that carbon always forms 4 bonds. So when we write CH3 or H3C, we're saying there are 3 single bonds to the carbon. That then single bonds to another carbon. That means the first carbon's used up all 4 bonds. Then it single bonds to another carbon, and then there's a bond to the next carbon, which is a triple bond. and the triple bond is made up of 1 sigma and 2 pi's. And then finally we end up the molecule with a CH. So if we're adding up the sigma bonds, we have 3 here, we have 1 here, that's 4, there's 1 in the triple bond, 5, and there's 1 here, 6. Let's check that. 3, 4, 5, 6. There are 6 sigma bonds. Pi bonds, well, the only place the pi bonds appear are in the triple bond, and 2 out of 3 of the bonds in the triple bond are pi bonds.